Alright, so in this video, I will be breaking the proof of this concept, that is the Cauchy-Schwarz inequality, in a very simple way for you to understand. If you are coming across my YouTube channel for the first time, subscribe to this channel, like the video, comment, and watch my other videos. Alright, so let's get started. The Cauchy-Schwarz inequality states that the square root of the magnitude of x, y is less than or equals to the inner product of x with itself dot the inner product of y with itself. So to prove this, you need to understand the inner product properties. Now, for vectors x, y, because x and y are two vectors, so we are going to consider the function of a real scalar t, that is, t is a real number. And considering the function of the scalar t, we are considering f of t to be the same thing as x plus ty, comma x plus ty. I'm just trying to make use of the positive definiteness property under inner product properties. Talking about this property. So now, if we have a vector like this, a function like this, a function of a real scalar t. Now, since the inner products are positive definite, that is, it implies that, I'm talking about this now, so it implies that f of t itself is greater than or equals to 0. So it is safe to say that x plus ty, comma x plus ty is greater than or equals 0. So this is the concept or the idea we're going to be using to prove this theorem. So now if you are to do something like this, you combine this, you combine this, and you combine this. How do we do that? The first one, you have x, x, plus the second part is x, ty, plus the third part is ty, x, plus the last part, which is ty, ty, or greater than or equals 0. Now, looking at this from the theorem stated earlier, if you have not seen the video on my channel. So now, for linearity property, this can be written as t, y plus t, y, x. And this also can be written as, you factor t out twice, you have t squared into y, y, greater than or equals 0. So furthermore, let's rewrite that here. We have x, x plus t into x, y into x, y plus t into y, x plus t squared into y, y, all greater than or equal to 0. Now, let's do something simple here. In the inner product space, you agree with me that y, x is the same thing as x, y. If it is for conjugate symmetry, you have this. This is the first property of the inner product. So if you agree with me that these are the same, then it is safe to say that when you add these together, you have 2 into x, y. So this can give you the absolute or the magnitude of x, y. So now, this simply can be written as x, x plus, when you add these two together, since they are equal, it gives you 2t into x, y plus this other part, since we have combined these two. So this other part gives you t squared into y, comma y, all greater than or equal to 0. So when you are dealing with something like this, it looks very well or very much like a quadratic equation because t has a power 2 here, t is standing alone here with 2, and t has a power of 0 here. So this is more or less like a quadratic equation. So if I'm to rewrite this equation, I can call it t squared into y comma y plus 2t, the absolute value of x comma y, plus x comma y greater than or equal 0. Now, let me quickly do something interesting. Let me set my a to be equals to y comma y. Let me set my b to be the same thing as 2 into x comma y. And let me set my c to be x comma x. So if I have this, then it means this part here can be written as, since y comma y is a, I can call it at squared plus, since the whole of this now is b, I can call it bt plus c, that's x comma x, greater than or equal 0. If you have a quadratic equation like this, the discriminant of that quadratic equation is such that b squared minus 4ac is less than or equal to 0. This is the form in which the discriminant takes. So, and that's, if we are to use the same idea on this concept here, we'll be having, since we are using b squared minus 4ac less than or equal 0. And don't forget that my b is 2 into the absolute value of x comma y. So I have 2 squared, then the absolute value of x comma y squared as well, minus 4 into a is x comma x. Sorry, a is y comma y, and c is x comma x. So almost the same thing here, since it's multiplication, less than or equal 0. And when you square 2, you have 4 into x comma y, inner space, squared. When you take this part to the right hand side, you have 4 x comma x, then y comma y. Now, they have 4 in common. When you divide all through by 4, you have x comma y all squared less than or equals to x comma x, then y comma y. Now, do not forget that these are square. So if you take the square or the square root of both sides, you have something like this. This means the square root will cancel this square, then you'll be left with this. You'll be left with the square root of this, comma this, and the square root of y, comma y. So this simply means that this expression can also be written in this form. The norm of x times the norm of y. Since this represents norm, do not forget that the norm of x is the same thing as the square root of x, the inner product of x with itself. So this inequality can still be written in form of this, and the theorem has been proved. So if you find this video helpful, subscribe for more. Thank you.